This is where we ended our last video looking at the typical learning curves by industry and typical learning curves by type of work. So it would be a great analysis for your project to look and see, for example, if you have inspection did a direct time study, do you see an 86% learning curve roughly? It's not going to be exactly. And if not, why not? That would be a great additional analysis, great analysis for your project. But let's move on to an example problem now and look at the learning curve equation, which you see right here, and then we'll go through this example problem here. So first of all, what this is saying the time for the youth number of output. I always laugh when I say that, reminds me of my cousin Benny. But let's say if we want to figure out the time for the 10th unit, it is going to be equal to the time for the first unit, is what K means, times 10, because I'm using 10 as my example here, raised to the N, and N is the log of the learning curve divided by log of 2. A log of learning curve, this really should be ln, and with the ratio it doesn't matter, but in reality when we do future problems it should be ln. But log of s, so log of the learning curve divided by log of 2. So the time for the 10th unit, for example, saying that u is the 10th unit, equals the time for the first unit times 10, because we're saying the 10th unit, raised to the power of n, where n is the log of the learning curve, divided by log of 2. So if we're saying 90%, the example problem we're going to go through, that would be log of 0.9 divided by log of 2 would be n. So let's read this example. It has been determined that a 90% learning curve applies to a particular assembly operation. It takes 30 minutes to assemble the first unit, so we already know that's our K is 30 minutes. How many minutes are required to produce the 5th unit and the 30th unit? So we're trying to figure out what is the time to produce the 5th unit. Will be 30 minutes, because that's what we're told is the time for the first unit, times 5 raised to the log of 0.9 divided by log of 2, and then we'll do the same thing, but just substitute 30 is really the only thing that we change here for the 30th unit. So let's go ahead and go through that problem. Let me pull up the PDF here. So we have our formula. We know that n is our log, and remember I said ln is really more appropriate for ratio. Either one works, but for future problems it's going to be a natural log of 0.9 divided by the log of 2. And you can see that that works out to be negative 0.152. You should always go back and validate my calculations to be sure I haven't made a mistake somewhere and that you can come up with the same information. So remember, important to note that through this example here, we're talking about a 90% learning curve. And so 90% learning curve was given to us. We didn't have to figure it out. That's going to be something we'll talk about, and that's what you'll do for your lab, is what if you're not given the learning curve? How do you figure out what that is? And you can figure it out from the time study data that you have. So if you have time study data from your project, that will be awesome. If not, you can use your flashlight time study data to, given the assembly time for units 1 through 10, what is the learning curve of that? Okay, so let's go through the first question here. What is the time to produce the 5th unit if we're given that we have a 90% learning curve? So we have z for the 5th unit, so the time for the 5th unit equals the time for the first unit, which is 30 minutes, times 5, because it's the 5th unit that we're trying to figure it out, raised to n, and we know from up here that n is negative 0.152. So that turns out to be 30 times 0.783 is 23.49 minutes. So to go from the first unit being 30 minutes, given a 90% learning curve, the 5th unit will take 23.49 minutes. And then I think, I forget, let me look, yes, okay, so then it asks you for the time for the 30th unit. So let's just jump down here. So the time to produce the 30th unit is 30, because it was 30 minutes for the first unit, times 30, because it's the 30th unit that we're trying to figure out, still raised to the log of n. Our learning curve is the same, 0.9 divided by the log of 2 gives us the negative 0.0152. So by the time we get to the 30th unit, it should take 17.89 minutes to complete the assembly of the 30th unit itself. We can also, just for, there's something called the doubling effect that I want to show you here. So we can find out the time for the 10th unit in the same way. It's the time for the 10th unit, so 30 is the time for the first unit, times 10 raised to the negative 0.152, which is the log of 0.9 divided by log of 2, is 21.14. What you'll find, though, for the doubling effect is every time we double the number of units, so from 5 to 10, from 10 to 20, we could figure it out this way using our formula, but the doubling effect says that the time between the reduction between unit 5 and unit 10, because that's double, is going to be the 90%. So 23.49 times 90% should also equal 21.14. That's the doubling effect. So let's show it down here with the 20th. So we go from the 10th unit to the 20th unit. So again, the time to produce the 20th unit is the time to produce the first unit, 30 minutes, times the 20th unit, raised to n, which we know from our calculations, is negative 0.152. That's 19.03 minutes. So we know the 20th unit, given a 90% learning curve, is going to take 19.03 minutes, assuming we had 30 minutes for our first unit. We can also use the doubling effect to figure that out, because 20 is double of 10. So if we take the time for 20, this 21.14 minutes, times 90%, our learning curve rate, that also gives us 19.03. So you can use this formula to calculate the time for the youth unit, or if you have the doubling effect, you can go from 10 to 20, for example, 5 to 10. You can take the time for the initial unit, the 10th unit, for example, multiply it by the learning curve, in this case 0.9, and find out the time for the 20th unit. Double of the 10 gives you 19.03. So that's the doubling effect. All right. Then another question we might want to know is, how much time is it going to take us to assemble the first... Let me look at the problem here to see what I did. The first 60 units. So what is the time to produce the first 60 units? So this is the formula that we use for cumulative time, and it's an approximation of an integral. So it's the time for the first unit multiplied by the 60th unit, in this case, whatever unit we're going to, plus 1/2 raised to n plus 1. N, remember, is log of the learning curve divided by log of 2. And then that gets subtracted by, in this case, the first unit. That's where we're beginning. So the first to the 60th unit, minus 1/2 raised to the n plus 1. All of that divided by n plus 1. So if we want to know the total time to produce the first 60 units, in this example, using a 90% learning curve, we have 30 minutes for the first unit, plus 60. 60 is our x2, plus 1/2 is 60.5, raised to the 0.848. That is our n of negative 152 plus 1 is 0.848, minus our x1, so where we're starting, in this case it's the first unit. The first unit minus 1/2 raised to the n plus 1, which we know is 0.848. All of that divided by, or enclosed here, you see, multiplied by 30, and then all of that divided by n plus 1. And so that turns out to be 1127.6 minutes, 1127.6 minutes. And if you actually were to plug the information into Excel, for example, and you could do this formula, it would be good Excel practice for you to do that. Plug this in and have a formula set up. You could have the time for unit 1 through the time for unit 16 added up. That adds up to 1,128 minutes. So you can see it's a very good approximation for the total time to produce the 60 units, the first 60 units. So why would that be important? Back to the reasons that we talked about for why we do a direct time study. We know how many people we need to bring in. If we need that much time, then maybe we can spread the work across workers. When we can commit to the customer that we would have those first 60 units done, those kinds of things. Okay, so something else might be important to understand then is, what is the average time for those first 60 units? And then of course that's just going to be the cumulative time that we have from above divided by 60. 18.8 minutes per unit is our average for the first 60 units. All right, so that answers the problem that was on the slide that I'll go back to in a minute. And then what I want you to do is answer those same questions, but for a 60% learning curve and compare them. So you answer those same questions on the slide for a 60% learning curve and compare. So let's go back to it here. So what we just went through was we answered how much time it takes for the 5th unit and the 30th unit, and the cumulative time and the average time per unit for the first 60 units given a 90% learning curve. What I want you to do now is to go through those same calculations with a 60% learning curve and compare the two, 60% and 90%. So it would be awesome for you to do that right now. Pause the video, but I'm going to go on and show you actually, I guess the first time you're seeing in this video series anyway, what the learning curve actually looks like. So this is the data from the 90% learning curve problem we just went through. We had the time for the first unit is 30 minutes. That's known as K in our problem formulation or equation. We calculated the total time for 60 units is 1127.6 actually minutes, so I should really have this as 1128, right? The average time per unit is 18.8, so it's 1127.6 divided by 60. And so the higher learning curve, so this 90% learning curve, is a smaller rate of improvement over time. So you can see the line is not all that steep, and you'll see what I mean when I move to the next slide that shows the 60% learning curve. So the learning curve of 90% is not that steep. That's saying that we don't have that much improvement from Unit 1 to Unit 2 to Unit 3 to Unit 4, etc. And remember that the inverse, this is why I said the learning curve versus the learning rate is important and distinct. I will always refer to it as rate of learning. How much improvement you have per unit is 1 minus the learning curve. So in this case, 1 minus 90% says that we have a 10% improvement, and it's not literally per unit, but 10% improvement for each unit that we assemble or manufacture. And remember, you know that this 10%, full 10% only happens when we double the number of units from our prior example that we talked about. So this is what a 90% curve looks like. And we went through the calculation for all of these with the PDF that I had up. So here is the information for the 60th. So you can see it took total time for 60 units is way less when we have a 60% learning curve. And what I want you to take away from this is you see the steepness of the learning curve here when we have a 60% learning curve, very steep, because the rate of learning, which again is 1 minus the learning curve, the rate of learning is 40%. So every time we double the number of units from 5 to 10, 10 to 20, we're going to have a reduction in time of 40%, not 10% like we had with a 90% learning curve. So you can see, because there's so much more learning taking place from one unit to the next, that our learning curve is very steep. Even though the percentage is small, the learning curve is steep. So how I like to think about it is 1 minus learning curve is the learning rate, and the rate of learning is bigger here, which equates to a steeper slope. You think about it however helps you remember, but that's what helps me remember. And then we can see the average time for 60 units is only 4 minutes when we have a 60% learning curve versus it was 18.8 for a 90% learning curve at the starting point. Okay, so again, you should go through, be sure that you can calculate all these out yourself so that you're practiced with that, and we'll do some problems in class. This is just the cumulative time, which the formula was on the PDF, which is also posted on PolyLearn, and then the cum average time is the total time divided by how many units. And then this is a side-by-side comparison, so you can see and compare the information. We went through all of these on the PDF, and then hopefully this is what you got when you went through the same calculations for the 60% learning curve. And we'll talk about this more in class, and I'll answer any questions you have for sure. What I'd like you to think about is it realistic that you have a very different learning curve and you have the same starting time? Could the same assembly process, have different learning curves? What would cause that if it can happen? Anyway, I think that's good discussion for us in class when you get to class. Okay, so that is the end of our second learning curve video, and we'll go back to talking about why some learning curve might have some interruptions and might actually asymptote out in the next video. Thank you.